Welcome to this IB Maths Intense session, our sixth video working with triangles under the topic of geometry and trigonometry. And in this video, we're going to be looking at the sine rule, which is a rule that appears in the syllabus under SL 3.2 and SL 3.5. There you can see it explicitly mentions the sine rule there, which give you a sneak preview of what the rule is. And it also talks about the ambiguous case of the sine rule, which is covered in SL 3.5. But we'll also look at that in this video. Just to apologise if you can hear gurgling noise in the background, that's my dishwasher going crazy, so apologies for that. So let's have a look and see what the sine rule is and how we derive it. Well, the sine rule is connecting the lengths of the sides of a triangle with the sine, the value of the sine of the angles in the triangle. And let's have a go at seeing if we can derive that ourselves without just using the formula as it's written. What we do know from our previous video is how to find the area of a triangle. And we know the area of a triangle is a half AB sine C. And we know we could have also found the area by using a different combination of sides and angles. We could have said it's also equal to half BC sine A. And we could have also said it's equal to half AC sine B. Those are the three different ways using an included angle and its two sides to find the area. Now here's a nice little trick. If I divide each of those terms by a half ABC, what we can find is half AB sine C divided by half ABC gives us sine C over C is equal to sine A over A. Again, if I divided half BC sine A by a half ABC, that would cancel down to sine A over A, which is also equal to, again, if I did the same with half AC sine B, I would end up with sine B over B. And there is the sine rule, derived from our formula for the area, but it tells me that the relationship between sine C and C, or sine C divided by C, is the same as the result I'd get if I divided sine A by A, or sine B by sine B. And if I want to, I can change this rule or formula so that the terms are the other way around. I can say C over sine C is equal to A over sine A, which is equal to B over sine B, because the relationship is still the same if I invert the fraction. Sine C over C equals sine A over A would also imply C over sine C is the same as A over sine A. So there are two different ways of writing the sine rule. You're only given one of them on the formula sheet, but you can use either, and you'll use the one that makes the calculation that you've got to do somewhat easier. There it is on the formula sheet, sine rule. And notice they give you only A over sine A, but don't forget you can change that round and make it sine A over A equals sine B over B, which equals sine C over C. They're the same relationship, and you can use either of those two formulae depending on the problem you're given. So let's have a look at some of the problems we might get. In the first case, we might be given a triangle where we've got two angles and one side. Now what's critical for the sine rule is that we must have a linked pair of angle and side. So we can see in this problem here, if we label the sides, I've got C over there, I've got A over here, and I've got B over here. I have got one link, which is I've got the angle at C and I've got the side C. So what I know for here, if I want to find the missing side B, I know that B over sine 54, that pair there, would give me the same result as C over sine 32. Notice I'm using the formula so that what I'm, and C is equal to 10, so let's put 10 in there. Notice I'm using the formula this way round because the unknown, the thing I want to find out, is a lot easier if that starts out on the top of the fraction. So just rearranging, b is equal to 10 sine 54 over sine 32, which gives me a result of 15.27 to 2 decimal places. As simple as that. Nice and straightforward example. Always easier to use the rule with the unknown on the top. It just makes rearranging it easier. Let's do a second example, just for good measure. So again, I'm going to just, before I start trying to work this out, I want the length BC, and I'll label that. That is the side A, and I've got the side B, and I've got the angle B. So I've got a pair there. I've got A over sine 100 is equal to B, which is 20 over sine 40. So rearranging, A equals 20 sine 100 over sine 40. Work that out in your calculator, and we get a result there of 30.64. Always good to just check the picture. Does that look like it's sensible? Yeah, well, the length BC, which we've labelled as A on this picture, looks like it's bigger than the length B of 20, so 30.64 looks like it's quite reasonable and sensible. Now, when we're finding a missing side, there's only one solution, and so that's nice and straightforward. You don't have to do too much worrying or too much thinking about it. But I'm going to introduce you now where, instead of being given two angles and one side, we're going to be given two sides and one angle, and we're going to try and find out the missing angle. And this is where we have to deal with the possibility of ambiguity, where there might be more than one solution. So in this picture I've got here, I'm asked to find the angle at A. I've got the side A, and I've got another pair here, which is the angle at B and the side at B. So I can write down here what I know. Again, I'm going to write down the thing I want to find out. I want to find the angle at A. So I'm going to write sine A over the side A, which is 20, equals sine of B, which is sine 35, divided by its corresponding side, which is 16. No problem. I'm just going to rearrange that. Sine A equals 20 sine 35 over 16. So A would be the inverse sine of 20 sine 35 over 16. And if I work that out on my calculator, it tells me that A is equal to 45.8 degrees. Now hang on a minute, because in this picture, the angle at A doesn't look like it's 45.8 degrees. It looks like it's an angle bigger than 90 degrees. It looks certainly not as an acute angle. And that's something we need to think about, because remember with our use of the unit circle, that if I have a value for my sine ratio, it's going to be positive in both the quadrant 0 to 90, so I had my angle of 45.8, but it's also going to give this a positive result in the second quadrant. So I need to find the second solution. So A could be equal to 180 minus my principal value, which was 45.8, which would give an angle size of 134.2 degrees. Now, if you look at the picture, the angle at A here looks much more like 134.2. So I'd say the solution here is probably 134.2, especially if the drawing is drawn to scale. If I was to draw the same triangle but with an angle of 45.8, I'm just going to try and sketch this here, it would look quite different. My side BC here would be 20. My side AC would be 16. It would be something like this. 16, there's A, and there is our triangle. This angle is still 35, but now the angle here is 45.8. So you can see there are two possible solutions to this problem. The picture just draws one of the two possible triangles, and you can see from the diagram it looks like it's 134.2 degrees, but there is a second case that would give the same angle side definitions, which is where the angle A would be 45.8 degrees. So you need to be careful for that there are often, when you're finding a missing angle, two possible solutions. So let's have another look. This time we're not given a drawing, which tells us that we need to be very careful because we don't know what our resulting triangle is supposed to look like. So find the measure of angle C in a triangle ABC. So I'm going to just sketch this. Triangle ABC, doesn't matter if it's not to scale or accurate. So my triangle ABC, just label the sides, the angles ABC, and you know that the length AC is 8, the length AB is 12, and the angle at B is 28 degrees. But it doesn't have to look like that. I've just drawn that to help myself determine what which particular version of the rule I'm going to use. So I want to find the angle at C. So I know that sine C over 12 equals sine 28 over 8. So sine C is equal to 12 sine 28 over 8. So C is equal to the inverse sine. On my calculator I can do this all in one shot, which gives me a result for the angle C of 44.8 degrees. And sure enough, on the little sketch, that would seem to fit. But we also know there's a second solution where C could be equal to 180 minus 44.8, which is equal to 135.2 degrees. Now, I do need to check that that would make sense in this particular triangle, because remember, angles in a triangle must add up to 180 degrees or less. 28 degrees is one of the angles, 135.2 is the other. That's possible. It's less than 180. So there are two possible solutions here, 44.8 and 135.2. And if I was to just sketch what that second one would look like, my side AC might look like that with 8, and my side AB, which is 12, is going to look like that, something like that. It's bigger, so my angle AB there is at B there is still, is still 28 degrees here. But now my solution for C is an obtuse angle of 135.2. So that would work too. So we've got two different triangles that meet the criteria in the question. This is the ambiguous case. Now, like I said, you always need to sense check whether both of them are possible. So here is a similar question, but this time with different values. And if we do the same routine, measure the angle, find the measure of angle C in a triangle ABC. If AC is 16, AB is 14, and the angle B is 54. So again, I'm just going to sketch it. Always good when you're doing an exam question to sketch the information you're given. We want the angle C, so I'm marking that. AC is 16 and AB is 14. And the angle at B is 54. So let's write down the appropriate ratio. I want to find the angle at C, so sine C over 14 is equal to sine 54 over 16. So sine C is equal to 14 sine 54 over 16. So C is equal to the inverse sine of that, 14 sine 54 over 16, which gives me an angle size between 0 and 90 degrees here of 45.1 degrees. Now before we said, but there might be a possible second solution. So we could say, well, C could also be 180 minus 45.1 degrees, which would be 134.9 degrees. And that seems like it's possible. However, look at the size of the other angle that we were given, 54 degrees. So 134.9 plus 54 degrees is bigger than 180 degrees. So reject this particular solution. Be careful of that. Reject this solution. So put a big cross through it. That's not possible. So there's always an ambiguity when you're finding a missing angle. So check that there are two possible solutions. Always check the larger solution to see whether the triangle would still be possible. In other words, the angles would add up to less than 180 degrees. So there we have it. That's using the sine rule, working with triangles in situations where we've got either two sides and a non-included angle, or we've got two angles and a side. I hope you found that useful. Thank you for watching. Don't forget to like this video and subscribe to my YouTube channel, IB Maths Intense. Tell your friends I'm here. Drop me an email at ibmathsintense@gmail.com with suggestions, feedback, any errors you might have found, things you might find useful. And in the meantime, stay healthy, stay happy, and enjoy your maths.